Okay, so we left off last time talking about some of the competing challenges involved in spreading tasks across multiple cores or processors. I just sort of listed out some of the things that came up in the discussion last time, and I think Tessa and I still need to figure out exactly the plan, but the basic idea for Monday in section is to talk through some of these issues in the context of particular examples. So you'll be hearing more about that as we flesh out that plan. And these things will come up, as we're talking about parallel processing, but also as we're talking about dealing with large data sets, which we'll start talking about today and then into Friday. Any questions from last time? So we basically left off talking about embarrassingly parallel calculations, where we can basically take a given computational task, split it up into a number of chunks, distribute those chunks to the worker processes, and then collect the results back with each of the computational chunks being essentially independent of each other, except for the collection back of the results. So the contrast to that is when you have a problem that's not an embarrassingly parallel problem, and you actually need to have the individual processes communicate with each other and pass information from one to the other. And once you start getting into that sort of thing, things get more complicated, and you need to worry about writing the code to basically manage that overhead of process number 1 needs to send something to process number 3, and then process 3 sends something to process 7, and you need to think about sort of what's the lag time involved in. If process 4 is waiting for process number 7, how long is it going to have to wait, and can I optimize such that it's not waiting very long, and these sorts of things. So you can do it. People certainly write code in that fashion. It gets somewhat more complicated and is a bit beyond the scope of what we have time to talk about here. But if you do get into doing that sort of thing, you'll likely be using this protocol called MPI, and there is an RMPI if you want to do things in R. Okay, so the idea for the rest of the parallel unit is basically to go through some of the basic ways we can parallelize embarrassingly parallel problems in R. And I'll mention that for a number of these, there are basically analogs to what I'm going to show you in R in software like MATLAB and Python. So if you see sort of the basic motif of how we do things in R, the syntax will be somewhat different and the concept's a little bit different in some other languages, but it won't be all that hard for you to map what you're seeing here onto the syntax in another language. So we've already, just to define a couple more terms, we've already talked a little bit about this idea of threading, that basically the operating system sees a given a threaded calculation is basically a single process, but you can think of as the work as being split up into a number of different lightweight processes. If you have forking, you're basically spawning child processes from the parent process, new copies of the parent process, and then the execution of the code in both of those processes, in the parent and the child, continues onwards. And we'll see that in a little bit. And then there's also this idea of sockets, which is basically a mechanism for communicating information between different processes. Okay, so we're going to look at something called for each, which is basically a parallelized for loop in R. And so there's basically something called the for each package, and that is basically provides a front end to doing parallelized for loops in R. And one of the notions of the folks who set up for each was that it can connect with different backends that deal with the sort of guts of how the parallelization goes on at the system level. So these are called the different backends, and so you can use for each either on a shared memory system, or you can also use it on a distributed memory system. And if you're using it on a distributed memory system, then the backend is basically RMPI, and RMPI is doing the communication of information between the different nodes in your cluster or your supercomputer or whatnot. So that's so basically, as long as you know a couple lines to basically set up the back end, then on the front end, at the for each side, you don't need to worry about exactly what the architecture is behind the scenes. Okay, and once we start up for each and start it running, what we should see if we're on a shared memory system with multiple cores is we should see multiple R processes carrying out our workload. So let's actually do an example of this. One of the things that I did here, I'm going to do this on Arwin, and I set OMP num threads to 1, so I'm not allowing any of the linear algebra to be threaded within each of the different worker tasks. The idea is if I were trying to allow that to be threaded, I would have 2 levels of parallelization going on. I would have the for loop that was breaking up the calculations, and then within each of the calculations, I would then have some threaded linear algebra that itself would be breaking up the calculation. So I'd have 2 levels of parallelization. So for one thing, that may not be all that efficient to have that sort of 2 levels of parallelization. And then the other is just there's this conflict that I mentioned between for each and the threaded linear algebra. So I want to make sure that doesn't happen here. So the only parallelization we're going to be doing here is across the different chunks of the for loop. Okay, so here we're going to load in a few libraries. We're going to load in the for each library. There are some other the for each package. We're going to load in the iterators package, which gets used in doing for each. And then we're going to load in parallel as sort of a core R package for doing parallel processing and provides a lot of functionality. So we need parallel, and then we're going to use this thing called do parallel, and that's basically the back end for doing using for each with multiple cores on an individual machine. So we just need to get stuff set up. Again, I'm doing this outside of RStudio because I'm just not quite sure what would happen in terms of the parallelization there, and it's easier and more transparent to just do it in a basic form. So this is a silly calculation. I'm just going to distribute out taking the mean of a very large number of random normals, and I want to do this. I want to do each of these things separately on separate cores. So I'm going to, for the moment, tell R that it should try and use 4 cores. So R1 has 32 actual physical cores on the machine, but I'm only going to use 4 of them. And I'm going to, this is basically setting up the back end such that for each can connect with this do parallel functionality to basically manage the distribution of calculations to the different cores. So I have to do this registration step. The registration step will differ depending on what the back end is, but you always need to do something of this ilk, this nature. If I were using do MC, which is basically pretty analogous to do parallel, I would do the registration like this, with register do MC and then the number of cores. And if I were doing this on a distributed memory system where I had multiple nodes, each with their own memory, I would have to use this code here to start an MPI cluster, and then I have to do register do MPI. Okay, so now I've basically set up the back end, and now I can go ahead and actually farm out the calculations. And the syntax looks a little bit different than we're used to with a for loop. Basically, we call for each. We have to iterate over. We're going to iterate over something. In this case, we're just iterating over the numbers 1 to 100. This is oftentimes not necessary because for each will often be smart enough about how to handle collecting and managing the results. But this is basically saying, as you get the results back, combine them together using the concatenate function as a single vector. So in other contexts, it might make sense if you're getting a vector back to combine the results by a C-bind or an R-bind or other sorts of things like that. And oftentimes R will be smart enough to figure it out on its own, or for each will. But in this case, I'm explicitly passing the function that I want to use to combine the results. And then I have this syntax %do par %. If you leave out the par, you can basically do debugging on a single core, just with %do, so the code will still run, but it will only do it on a single core. But once we have the do par, it'll actually do it in a parallel fashion, assuming we've set up the back end correctly. And then this does, I haven't really done very much here, except I just put in a little print statement to say I'm starting a job and ending a job. I call the task fun, which is the core calculation that I'm planning on doing. And then basically, like an R function, whatever the last line is, whatever the result of that is going to be sent back to the master process, and this is what's going to be combined via in this case, the concatenate function to create the out object, which should end up just being a vector. So any questions about the syntax or the context of what I'm doing here? Okay, so what we should, let's pay attention to a few things as we do this. What we should see is basically a scrolling set of starting and ending print statements, and we also should see 4 cores starting on R1 here. So here's top. There's a little bit of a delay, and I don't have this big enough to see all of them, it looks like. But you can see it's working its way one by one through the tasks, and indeed you can see that hopefully you can see that there are 4 jobs that I'm running here, each of them running at about running right around 100%. Okay, so I've successfully divided up my job, distributed amongst the 4 tasks, and basically our for each is managing the process of sending out 4 jobs, and then as individual ones of those return, it sends out another one to whichever core whichever process or core is free. So we're marching along. We're almost done. You can see that they're sort of out of order, so R is not dispatching these things necessarily in order, and they take a little, slightly different amounts of time to finish. So the 100th job got dispatched and finished before, say, the 99th job. So things are not totally in order in that sense. And then if we look at out, it indeed has collected the results back as a vector of 100 values.
So when you collect back, would that be in the order of 1 to 100, or that would be?
Yeah, so that's a good question. In some cases like this one, it may not matter what order we get them back and whether they're sorted in the correct order in which I dispatch them. In other cases, it might actually matter. So I believe there's an argument with for each that, so there's a dot in order argument, and this is basically this question of is the dispatching and the results in the same order. So the default is true. I suspect there's a little bit of overhead in managing that, so it might be that if you set this to false, it might speed things up a little bit, although I would guess only marginally. Okay, other questions? Yeah. How what?
Seed.
Oh, yeah, the random seed. So the sort of nitty-gritty I've swept under the rug here is we haven't talked about whether we're setting separate random seeds on for the different tasks, and whether we're actually using a separate stream of random numbers for the different tasks. So I'm going to basically defer all of that until we get to the simulation unit, but it's an important question and one we want to think carefully about. Did you have a question about it?
Yeah, I would ask, instead of combining or having the function combine using cbind or c or something, if each iteration was going to give you like an array, and you wanted to put that to be like a row of a matrix, would you be able to just call the function into the loop and assign it to a specific row of a predefined matrix?
Yeah, I don't think you can do that because basically all of these tasks are operating independently. They don't have access to sort of the master object that you're trying to create at the end. So I guess the way that I would do that is if I really had an array coming back, let's say I had, just for the sake of being crazy, I had a 4D array coming back. I would basically, I think what I would do is basically vectorize that, create a flat vector out of that, pass that back, use cbind or rbind to create a matrix as a result of that, and then at the end, with the out result, if I really wanted to create a 5-dimensional array of, say, 100 results with 4-dimensional arrays, I would then coerce that into an array from there, is probably how I would do it. There might be a more sophisticated way to do it, but that's probably the most straightforward. Other questions? Okay, one thing to be aware of here is that what R is doing is basically creating an independent copy of whatever data you have that you're using on for each of the tasks. So you could have your memory use increase quite a bit when you do this. I was sort of phrasing that a bit hesitantly because I'm realizing that there are arguments to. Let's go back to the arguments to for each. I've never sort of quite figured this out. Sometimes you need to basically tell R what packages are going to be used within the task fund, within the individual calculation that's being done in each of the cores. And other times it seems like it may not actually need those. So I've never been totally clear about sort of what you need to give to each of the worker tasks. And you'll notice there's also this .export, which is basically saying what object should I export to the worker tasks. Except it seems like when I've used this before, it hasn't always been necessary to be explicit about which ones to export. So let's see what it says on help here. So character vector variables to export. So these are the variables that you want the worker processes to be able to access, to be able to do work on. So, oh, I see. So it says when a variable that isn't defined in the current environment. So presumably everything in the current environment is going to get copied over to the worker task. But if there are some other things that are not in your current global environment that you want to pass along, could do it with this .export. And then this .no export is presumably a way that you could, if you had some big object in your global workspace that you didn't want to be copied over to each of the tasks, because that would then blow up your memory use. Presumably, I haven't tried this in a while, I don't think, but this should work if you said .no export and give it the name or names of those objects that you don't want to copy, to do that to reduce your memory use. Okay, so for each is a workhorse if you're doing parallel calculations. There are a few other basic, there's lots of different ways you can do parallelization in an R. We're only covering a few of them. A couple of the other more basic ones are basically doing a parallel version of apply or lapply or sapply, and then doing parallel vectorized calculations. So let's go ahead and look at doing parallel applies. So I'm basically going to, again, use the parallel package. I mentioned this has a lot of sort of the workhorse routines in it for doing parallel calculations. Let me just quit out and sort of get a fresh session here. Okay, so now I'm going to, in order to do a parallel sapply, which you can see lurking down here at the bottom, basically if you think of all the different apply functions, apply, sapply, lapply, mapply, there are sort of parallel versions of many of those, and they're often of the naming convention like par sapply or par lapply or things like that. And if you want to get help on all of that, all of those different various applies, that's not going to work because I need to load parallel. You can sort of in all its gory detail see all of these various different parallel versions. As you can see, there are like 10 or 15 of them. I don't actually know exactly all the distinctions between these, but in some cases some of these might be helpful. But you can go a pretty long way with just knowing the basic ones. So we're going to have to basically use this function called make cluster that sort of sets things up and sets up the communication amongst the different processes they're going to get created. So I'm going to do that. Okay. And then I'm going to, again, my test fun is, I guess I called this task fun before. It's just going to generate the mean of random normals. If I just type CL, the object that got returned from make cluster, it should say a little bit about what the nature of the parallel setup that's been created. Notice that it says there are 4 nodes, but they're all on host localhost, which basically just means my local machine, so they're not distributed across different nodes in any sort of cluster. And now I'm just going to do an sapply where I use the cluster I've set up. I'm doing the sapply over 1 to number of sims, and I'm using the test fun. So this looks like an apply, an lapply, sapply kind of statement, but it's in this parallel context. And if I do that, I should again see multiple R jobs running, each at about 100%. Looks like that was pretty quick, so that vanished pretty quickly. It's interesting that the user time was so little. I'm not actually sure what's going on there, except maybe all the time was in the sort of communication and setting things up. Sometimes if you want to get objects to the worker tasks, you actually need to call a cluster export and explicitly say what the objects are that you want to send out to the worker processes. And let's compare the timing to just doing an ordinary sapply. And here we should just see that there's only one R job running. Here it is, the second line, third line there. Obviously, it's already taking rather more time than the parallel version did. So in this case, it took 10.8 seconds compared to 3 seconds. Yeah, I'm still quite befuddled by this fact that this is so small. I'm not quite sure why. Maybe somehow, maybe what's happening is system.time is not actually tracking the computational time that's getting used by the worker tasks. And so all it's doing is calculating the amount of time being used by the master process, which is minimal, because all it has to do is dispatch the results, dispatch the work, and get the results back. So that would be my suspicion of what's going on here. And we can see we didn't quite achieve a 4-fold speed up. Remember, we have 4 cores running for this parallel supply, but we got fairly close. And if you wanted to do a parallel lapply, you can do it with similar kinds of code. So here I actually created a list and did a par lapply. There's also a version of parallel lapply called MC lapply, which is pretty similar to par lapply or par sapply. The syntax is a little bit different, but you basically give it a test fun. Here I'm iterating over the number of sims, so 1 up through the number of sims, and I'm saying how many cores there are. So I think for this, I don't need to do the creation of that CL object. I think I can just run it like this. And we should see again that things are reasonably quick once we parallelize. So yeah, so that was more or less the same amount of time as the par sapply here. You'll notice it actually seems like it did a decent job of keeping track of the actual total computational time in this case. So something different behind the scenes must be going on in terms of whether system.time is able to keep track of what's going on. Let's look at the help on MC lapply. I want to point out one thing that it does that gets back to these sorts of questions of how we manage the distribution of tasks to processes. So there's this argument called mc.preschedule. And this MC that's actually sort of a side note. This mc.setSeed has to do with setting the random seed, which Yang was asking about. So I think we'll come back to that in the simulation unit. But here's this mc.preschedule, which is interesting in light of these sorts of questions. It says if it's set to true, then the computation is first divided to as many jobs as there are cores, and then the jobs are started, each job possibly covering more than one value. So if I have 60 jobs, it's basically saying 60 tasks, and I have 4 cores, it's basically saying I'm going to divide up those 60 into 15 each, send off a chunk of 15 jobs to each of the 4 processes, and collect the results back. If it's set to false, then one job is forked for each value of x. And it says the former is better for short computations or a large number of values of x. The latter is better for jobs that have a high variance of completion time and not too many values of x compared to the number of cores. So when it's talking about this high variance of completion time, think about what happens if I send off 15 jobs to each of the 4 cores. And suppose some of those jobs take a lot longer than other jobs. Well, what could happen is I might end up getting one or more very, very long jobs on one of the processors. And it's running along and it takes a long time. Meanwhile, the other 3, or some number of the other 3, have already finished because they have the shorter jobs. And they're just sitting around doing nothing while this one processor is churning away on its harder, more computationally intensive task. So in that case, setting preschedule to false would presumably be advantageous because then we dispatch 4 jobs. Suppose that one of those is a very slow job. Well, it keeps churning away, but when the other 3 finish, the next 3 jobs are dispatched to them. So we have better load balancing across the computations that we need to get done in that case. On the other hand, if all the jobs take essentially exactly the same amount of time, we might as well just only communicate out 4 times to the workers, have them get all 15 that they need to do, and have them just start working away instead of having to do this. Are you done yet? Okay, I'm done. Here's the stuff. Here's your next job. You know, this sort of having to do this additional communication and management. So that's one of the things that's going on behind the scenes here in terms of making decisions about how we split things up. Questions or comments? Okay, so then we can also distribute out a vectorized calculation. So again, I'm going to use some functionality in the parallel package. I'm going to make a cluster again. In this case, I'm going to load a library in called fields because it has this matern function, which is basically a correlation function. It turns out, let me clear out here and just start over again, so I don't have to worry about whether I have to close down clusters and whatnot. So I don't want to go too much into what this is doing, but the main point here is this matern function that if I just did it in serial fashion would look like this. It's a fairly intensive computation. It involves some Bessel function calculations behind the scenes. So this is a vector, and this is the distances, basically. And this is basically going to compute the correlation as a function of a whole bunch of different distances for some additional parameters. This is a parameterized correlation function. So we can either do that in serial, or there's this pvec function that will basically take a vector, split it up into chunks, dispatch the chunks of the vector to different tasks, to different worker processes, and then carry out the calculation on each of those chunks, and then recollect the pieces. And we can see whether or not that might be worthwhile in this context. Oftentimes this is not going to be all that helpful because a lot of the vectorized calculations in R are already pretty quick, and so the time involved in sort of breaking things up and sending them out and collecting back may not help you that much. But we can see in this case, I think I was, I'm not sure why it's doing that. So anyway, things are probably fine. So here we should again see 4 R jobs, 4 tasks under my username running here. It looks like they are indeed. Looks like they finished. So that took about 3 seconds. And then if I just do it serially, let's see how long it takes. Well, it looks like it is going to be worthwhile in this case. So you can see that the speed up is not as impressive as when we did the par sapply. We've only got about twofold speed up, even though I'm using 4 cores here. So apparently there is a reasonable amount of overhead involved in doing this. And I would presumably need a fairly long vector and a fairly intensive calculation in the vectorized calculation to make this, for this to be worthwhile. So in this case, I did sort of set this up so that would be the case. You know, I have a reasonably long vector and I have a reasonably intensive calculation I need to do. If either of those conditions were not true, I might not see that it was worthwhile to do this. Okay, and then the last thing I want to mention is a couple other pieces of functionality that where we were doing sort of more explicit parallel programming that involves us doing a little bit more management of what the tasks are. So there's also something called MC parallel, and that would actually allow us to basically dispatch a job, dispatch another job, and then sort of collect the results back in a more manual fashion. So suppose for some reason I needed to generate a whole bunch of random normals and calculate their mean, and I needed to generate a whole bunch of random gammas and calculate their mean. So I have 2 sort of separate discrete tasks. And you know, these are going to take a little bit of time because n is large. So what I can do is basically call MC parallel with the calculation I want to do, assign the results back to 2 different objects, and then say MC collect on those objects, and that will basically collect the results back. So what should happen is basically R should dispatch that work, and then the MC collect should basically wait until it's able to get the results back from the workers. So we can see that takes a little bit of time, and if I just did this in serial, again, we can play games with just doing a little bake-off and seeing how long each of these things takes. And again, the question would be, one question is, so how close are we to getting a 2-fold speed up? In this case, we actually got fairly close in this case. So for any given calculation that you have, this would actually be a fairly easy way to say, I'm running through a calculation. I have to do 2 calculations that are basically independent of each other, but I can't proceed until I get the results from both of those calculations. I could set it up with this code, and as you've seen, this is basically a one-liner in terms of what I have to do to manage that. And then the last thing I'll show you is just the process of actually creating an explicit new child process. So I don't know if this would come up all that often, particularly as you're starting out, but I just want to show you the sort of motif of what the code looks like, because when you do forking in other languages, the code often has this sort of flavor to it. So I can call the fork package up there at the top, and there are basically 2 modes of doing this. I can either call the fork function within the fork package with a particular function that I want to evaluate in the child process, so that would be one mode. But the second mode is the sort of way that fork code that does forking often looks like in R, but also in other languages, is you basically do a fork. In this case, I say null to say that I'm not going to execute any particular function on the child process. I get back the PID of the process that got forked, the duplicate process that got created from the parent process. And then basically what you see in this kind of code is you have to have an if clause that basically says, am I the child or am I the parent? Because once you do the fork, you've now got 2 identical processes that are running. They have copies of the same objects, and they're going to run the same code from this point onwards. So all of this code will get run in both the child process, the fork child process, and in the parent process. So we need a way presumably want different children or the child and the parent to be doing different things. So we need a way to distinguish these. So you basically need to have an if statement that says, okay, am I the child or am I the parent? If I'm the child, which in this case corresponds to PID equal to 0, then I'll do this. If I'm the parent, then I do this other stuff. So that's the sort of way that you would generally write code where you're actually explicitly forking stuff. This code here is pretty clunky because I'm not really managing the communication of results back from the child in a very sophisticated way. I'm actually writing out to a file. But I did want to just show you that sort of style of what code looks like when you end up running a fork. Okay, so I think that's all I want to say about parallel processing. Although we're going to come back and touch on it in the simulation unit, and it'll come up probably some in the next unit where we're talking about databases and big data. Any questions before I move on to the next unit? Okay, so this is Unit 9. It's going to be another fairly short unit. And basically what we're going to see is various ways of working with fairly large databases or data set sizes. So I'm going to start off and explicitly talking about actual databases, relational databases. And then we'll talk about data files that are too large to read into memory in R and some of the functionality that's been set up to handle that. And then we'll talk about a little bit about some algorithmic questions related to big data. Okay, so there's a little bit of an editorial here on my part, which is that everybody's heard of big data and there's sort of a hype about it over the last few years. And I just want to I'll let you read this on your own time, but I just want to make the point that just because I have a large data set doesn't mean I'm in any way getting around all the problems that usually occur with data, which is there's going to be measurement error in the data and potential biases from that sort of thing. There's going to be the issue of correlation is not causation. We're not going to directly get around that by just having a larger data set size. We're just going to still have a biased answer to our question. We might have a very precise biased answer, but we're still going to have a biased answer. That just because we have a large data set doesn't mean that it's a representative sample relative to some population that we're interested in asking questions about. So having a big data set is going to drive down variance in general, so we're going to get more precise answers. And in terms of causation and having good statistical samples, it might allow us to be clever about sort of subsetting the data and selecting out data that will give us a better answer to the question at hand. But it doesn't directly address a lot of the issues that we've needed to deal with from a statistical perspective for decades. Okay, and then I'll just say that in terms of what do we mean by big here, the sorts of things we're going to, some of the techniques that we'll talk about will deal with fairly big data sets, but I'm not really talking about dealing with sort of enterprise scale data of the sort that if you were working at Google or for the NSA or one of these sorts of organizations that you would be working with. So we're sort of more talking about gigabytes kind of scales here than we are talking about terabytes or petabytes. So I'll just make that note. Although, some of the techniques that we'll talk about are relevant for those even larger data set sizes. Okay, so a couple of general comments. One is about R, which is that one of the main drawbacks with R for working with large data sets is that data in R naturally is worked with in memory. And so we're limited by the actual physical memory we have on a machine. So depending on how much RAM you have in your machine, that could be limiting you down to data set sizes that are 500 megabytes or a gigabyte, or if you have a lot of RAM, then maybe you can get up to 10, 20 gigabytes of data that you could load into memory. But once you get beyond anything like that, you're going to start running into real problems. And then the other point is that oftentimes it's going to be helpful to actually have the data on the local disk that's attached to the actual computer processor that's doing the calculation. Because otherwise, oftentimes, your bottleneck is going to be transferring the data over the network to the processor that's actually going to do the computation. So that's one thing to keep in mind as we talk about these questions is, do I have a local disk where the data are residing where I can do the computation right there, and limiting the amount of situations where you're doing a lot of data transfer. Okay, so one other comment that I'll make here is we've actually already learned a number of tools that are actually quite useful for handling big data sets, and that was part of my goal with what we did in the first couple units, where we talked about a lot of the Unix operations and piping stuff and not unzipping stuff and doing stuff all as basically a stream of operations. That a lot of the basic Unix tools are very fast at handling many files and large data sets, either from a single file or from making a large data set from many smaller files. So a lot of those tools can be quite helpful. And as we have already seen, you can do a lot of subsetting by column or by row using some of the tools that we've seen and some of the things that people have discovered, even though we didn't really cover them, such as awk, to basically subset data before you then get to the stage of actually doing an analysis. Okay, so let's talk about relational databases. So the basic idea of a relational database is that we're going to store data as a set of related tables. And so each of these tables is sort of like an R data frame. It has basically observations, and it has fields or columns, and each of those fields has to have only a single type in it. So we might have a name field, and we might have an age field, and we might have an income field, or whatever else, and the sort of things that we're interested in. But the idea of a relational database is that that oftentimes we basically have sort of a hierarchy of information, and it doesn't make sense to store everything as just a single flat row by column data set size. So let's just work through a basic example of this. So suppose that I have a database that suppose I'm the registrar at the university. Right? So what sort of information do I need to keep track of? I have information about students and what the characteristics of each of the students are. I have information about what classes each of the students is taking. I have information that's really sort of more specific to the classes, like who the instructor is and how big the class is and things like that. What room the class is in, for example. And then I have information presumably about the instructors, how many other courses they're teaching, how many years of experience they have, what department they're in, et cetera, et cetera. So I have all this information. And if I were to store all that information in a single data frame or a single table in the relational database terminology, we can think about what that would look like. Right? Suppose that I'm thinking about storing it based on the students as the sort of unit of information. So if I think of each of the students as an observation, what is this going to look like? I'm going to have the student, student A, student B, student C. And then presumably each of them is taking a number of different classes. Right? So I can say, okay, well and here it already starts to get a little bit messy. Maybe they're not all taking the same number of classes, so I get some raggedness in the data. But for the sake of simplicity, let's assume they're taking no more than 3 classes. So I can say, okay, class 1, class 2, class 3. And now I can think about, well, what are the additional columns that I would have? I might have the information of what's the teacher of each of those classes, right? Okay, so, well, now it starts to get a little messy because now I've got teacher 1, teacher 2, teacher 3, right? So I should make a little more room here. Actually, we could think of it as a very large table, and I could retype in the room operations on the other side of the screen. All right, so class 1, class 2, class 3, teacher 1, teacher 2, etc. Okay, so first of all, does anybody see any issues with having a whole column of teacher 1, teacher 2, teacher 3? What's one of the disadvantages of doing this? Okay. Right, so suppose student A is taking 243 and student C is taking 243. Okay, then teacher 1 becomes me, once, and teacher 1 becomes me again. This is redundant information. I already know, as long as there's a unique teacher for each class, I already know what this is without actually having to fill in this value. I'm actually saving all that information. And okay, now suppose we've got, say, the age of the teacher. So I don't know why I keep using age as an example, but okay. Okay, so suppose I were 25 years old. So we've got 25 repeated multiple times, but then suppose I have a birthday. Right? Then what happens? I have to go in and change the information, it's really kind of stupid to have to go in and change each of the 25s associated with each copy of me to be 26. You know, that's going to be prone to errors. It's just going to involve a lot of computation that I don't need to do. Okay. So you can imagine if we were actually doing this, the actual number of fields would, you know, zoom on out to the other end of the board, because we have all this teacher information and all the class information stored in this this big flat file where things are stored in a redundant sort of way. Okay, so the basic idea of a relational database is we're going to take this information and try to eliminate that redundancy, and basically do that by having a number of separate tables. So I can do that by having a student table and a teacher table and a class table, for example. And now I've got student A, student B, student C. I would presumably still have class 1, class 2, class 3. So maybe this person is taking 243 and this person is taking 243. But now I can have a class table, and I could have 243 and 201A and 201B and whatever other classes are being offered by the university. And within this, I guess I'm not sort of labeling all the fields very well. So this would be sort of the ID field. And now I can have a teacher here. I honestly think is teaching 201B, et cetera, et cetera. And now I could, you know, okay, so now I presumably only want to have class level information here. So I could have the enrollment, for example, et cetera, et cetera. And now I can put all the teacher info, the stuff that's specific to each teacher, in the teacher column. So I can have each of the instructors, and here I could have, so here's the instructor name. Here I can have age or experience or whatever, and so on and so forth. So now a couple things. One is I've eliminated a lot of redundant information. Each of the tables is sort of simpler conceptually. And if I want to go in and make changes, you know, if the instructor's age changes, all I need to do is go in and make the change in this unique location. So that's basically how these relational databases are set up. Any questions at this point? Of course, there are going to be lots of times I need to go back to something that looks like that. For example, if I want to do an analysis, I might need to actually, if I want to do an analysis, say at the student level, I might need to actually get back, you know, the names of the instructors for each of the students or something like that. And in that case, I'm going to need to do some merging across, or joining in the database language. I need to do some joining across these tables in order to get back a sort of single flat set of information where I can actually have the usual observations and rows and columns and things like that. So that is, you know, set up more to do statistical analysis. This is set up more for doing fast querying and for storing the information. And the other thing that I want to mention here, getting a little bit ahead of myself, is this idea of having keys, which are basically either one or more columns that basically uniquely identify each row in the database. So in this case, the key for students might just be their name. On the other hand, if we have, you know, for example, 2 John C. Smiths, we would need to have a different key that was not just their name. We'd need to have some identifier that maybe it was their name plus their student ID, or maybe the student ID is unique and that would be the key. Okay? So this might or might not be, the name might or might not be the key for this table. And then we'd need a key for this table, which again would presumably be the name or something related to the name, maybe an employee ID number, something like that. And then here we'd need a unique identifier that would presumably relate to what the class number was. Of course, in this case, we'd probably need to add on department to make it a unique ID in that case for that to be the key. So this would be, so we'd have these keys, and the other thing is this notion of a foreign key. And so a foreign key in the student table would be a column that in another table is the actual unique key that identifies information in the other table. So for example, one way people sort of represent this pictorially is they'd say, okay, guess I've sort of set this up in a little bit of an awkward way, but for what I'm about to draw. But the key in the class information is this ID, and then that we would have a foreign key in this table for the class information that would basically allow us to join information from the student table to the class table. And then similarly, we would have a foreign key in this for the teacher that then allows us to link to the teacher table. So that's the idea of these keys. Okay, so there are a whole bunch of different database management systems put out. Some are free, some and open source, some are big company products that allow us to allow people to basically manage these big databases. Some of the systems are Sql Lite, MySQL, PostgreSQL, Oracle, Microsoft Access, et cetera, et cetera. A lot of them are built around a language called the structured query language, which is basically sort of the main language for writing database queries and managing databases. And basically variations on SQL are used in a lot of these different database management systems. So many of the database management systems are basically set up as a client-server operation. So there's a server that's sort of doing the management behind the scenes, and the clients connect to the server and say, I want to do a query, and I want to pull out the information for everybody in one class and pull that information back. And so you need to sort of authenticate with the server and get, send the query to the server and get the information back. That's sort of more high-powered than we'll need for the class and even for a lot of what you guys might need in your everyday work life. So we're going to focus mostly on something called Sql Lite, which uses SQL but is basically something that you can set up just on your own machine and doesn't have a lot of issues with authentication or having to contact a server and collect information back. So the database is actually, even though it's going to have multiple tables in it, it's actually going to be stored just as a single file that we can then do queries against. So the other thing to know about these database management systems is, like we had with the parallel processing, where there are these different backends, but there's sort of a common interface that allows us to easily interact with them. In languages like R and Python, there are basically ways that we can interact with the backend using a common set of syntax on the user side. So there are command line interfaces to different database management systems, but often the easier way to do it is actually to do it from within a language like Python or R. So we're going to see that from R. And our example is going to be a data set that's available on the SCF machines at this location, just on the file system. And basically what it is a bibliographic database of basically information on essentially almost all statistics journal or statistics-related journal articles that have been published over the last 100 years or so. So you can imagine that if you think about setting up a bibliographic database, you've got these journal articles with titles and journal names and authors and information like that. You can imagine setting it up something like this. Like you might have information about the individual journals, like who's the publisher and that sort of thing. And you might have information about the individual authors, like what their affiliation is and where they work and whatnot. And then you might have information about the individual journal articles, about the title and which journal it is and who the different authors are. So you can imagine setting up a similar set of tables in that context to what we laid out as an example here. So when we pick things up on Friday, what we'll see is an example of using R to interact with that SQL Lite database of journal information, which is set up in that fashion. And we're done.